Hi, this is Guillermo Campitelli, and in this video I'm going to continue with the case of a nominal variable affecting a numerical variable, and this is a within subjects design, and we are going to see now the model comparison approach and the hypothesis testing approach. So within the model comparison approach, we start with maximum likelihood and then we go to base factors. Okay, I did the analysis with R, and basically I used two models. A model that says that there is no effect of the variable documentary, and another model that says that there is an effect. Now, this for doing model comparison, it's a bit tricky because what we've done in the between subjects designs is to use a linear model for do model comparison. And linear model has the assumption that the observations are independent. And that assumption is not met in the within subjects design. That's because the four observations that contribute each participant, those four observations are not independent. They are they come from the same individual. So because while that assumption of independence is violated, then we need to do something about it. And there is a way of doing it, which is to use the variable participant as a variable. But so we've got 200 participants. Now, each participant is a unique case of the variable participants. So it is like a nominal variable. We can call it participant 1, participant 2, participant 3, but these are not numbers. It's just a code. So basically, each participant is a category within a nominal variable. And remember what we've done in the between subjects design with our nominal variable documentary. We transformed it into 3 dummy variables. Okay, so we have to do the same with participants. We transform the variable participants into 199 dummy variables. 199 is the same as the reason why 199 and not 200 is the same reason as why we created 3 dummy variables for the documentary variable, and we don't need the 4th. And so we do the same with participants. We create a dummy, and basically the dummy code is we put a 1, let's say create the dummy variable for participant 1. We are going to put the values, value 1 to participant 1 and value 0 to all the other participants. Dummy variable called participant 2, everybody has a 0 except participant 2, who has a 1, and so on and so forth. Now, this is in the two models. So basically here, model 0 and model 1 are exactly the same as model 0 and model 1 in the between subjects design, but we added this term, a vector of gammas and a vector of participant dummies, and the same we did in model 1. So basically, when we've got this involved, means that instead of being just one of these, it's a vector, so a number of gammas. So basically we are going to have a gamma for each participant dummy. And again, participant dummies is not just one, is a vector of participant dummies. So this will be 399 gammas and 300, sorry, it's one per participant. So 199 gammas and 199 participant dummies. And the same here. So basically that's the workaround to deal with the issue of independence. We create a new variable, or 199 new dummy variables. So in this way we solve the problem of independence, lack of independence rather. Okay, so I use this model. So basically the model in model 0 we would estimate parameter beta 0 and all the gammas, and model 1 will estimate beta 0, beta 1, beta 2, beta 3 and all the gammas. And then after the estimation we get mu's for all the 800 observations, and then we which are the predictions of the models, and then we compare that with the actual values. We determine for each value how likely it is in a normal distribution with the predicted mu, and then we come with we multiply all the likelihoods, or rather we add all the log likelihoods, and we come up with the log likelihood for the model, and then a deviance and an AIC. So first of all, I show you the R square, which is the measure we used in the most traditional approach, in the error minimization approach, to show you that the within models that I showed you the formula just now are better than if you don't include the dummy variables. So model 0 and model 1 is the model that doesn't include that don't include the dummy variables. So we shouldn't do it because it's incorrect. We are assuming independence when there isn't, but we can actually perform the analysis. And you can see that model 0, the R square, so the variance of the data explained by the model is 0, because we use only one value to predict the 800 values. And model 1 accounts for a lot of the data, 0.976. Now, when we have model 0 within, which includes all the dummy variables, we increase from 0 to 0.006. Very minor increase. But when from model 1 to model 1 within, again including all the dummy variables, we increase from 0.976 to 0.982. So it predicts the data better. But remember that we need to account for these extra 199 parameters that we estimated. So that should be penalized. And you are going to see that the AIC of, you can see model 0, 8008, but model 0 within, even though it predicts the data better, the AIC is higher. That's because of the penalty the model receives for having 199 extra parameters. And model 1, again, is worse in terms of predicting than model 1 within, but the AIC is lower, so therefore it is a better model. But we cannot use model 0 and model 1 because they are violating the assumption of independence. So we have to use model 0 and model 1. And so basically, model 0 within and model 1 within. So this is the comparison we make, model 1 within against model 0 within, and it's a huge difference between the two, huge difference between the two models. The lower AIC is for model 1, so that shows that model 1 is a much better model than model 0. Model 1 within, much better model than model 0 within. Okay, so now I'm going to explain the base factor approach, and for that I'm going to use JASP. Okay, so what I'm going to do in this case, I can, as I mentioned many times, hypothesis testing is a type of model comparison. So if I wanted, I just showed you the model comparison I will do in the hypothesis testing approach. So in this base factor for model comparison, I try to come up with things that you can't do with the traditional analysis. Okay, so in this case, we want to test two theories. A theory of a researcher that believes that the we are taking as an example the difference between poverty and gardening. So just these two conditions. So a researcher says that the expected difference is minus 56. And another researcher has another theory, and that theory determines that the difference is of 53. So one says minus 56, the other one says minus 53. So basically we can now compare the maximum likelihoods of two models to determine which one is better predicts the actual data. Okay, so there is a technical issue. So I'm going to start with JASP and I'll show you what's the technical issue. Okay, so we've got the data here. What we are going to do is to go. Sorry, so we shouldn't use this data set. We should use the data set of the difference scores, the one that I created. Which is this one. So remember, I created 6 variables, which are the difference scores. So for each subject, we calculated the difference between one condition and another, and we did that for the 6 contrasts. Okay, so now instead of going to what we did before, now we do Bayesian one sample t-test. So we are doing base factors, we are not using the traditional method, so Bayesian and one sample t-test. And here you got the test value, so you compare the actual mean of these variables. We are going to use just one, so basically the difference between poverty and gardening. So we select and we put poverty and gardening there, and here I calculated a base factor, but this base factor is against the value 0. So obviously it's much the value is minus 54, the mean of this variable, so very far from 0. So you've got a very huge base factor. But we need to do two things. First of all, change this test value. So the test values we have to use is minus 53 and minus 56, which are the theories of the two different researchers. So let's put minus 53. So basically what we are going to do is we are going to obtain the base factor for minus 53 and the base factor for minus 56. And then we compare, we obtain the ratio of these two base factors. Because if the base factor of minus 53 is compared against the same marginal likelihood, so if both base factors are compared against the same marginal likelihood, then obtaining the ratio of the two base factors gives us the base factors of these two models. So basically what we are doing first is to calculate compare the minus 53 against an alternative model and minus 56 against an alternative model, and we obtain the base factors. And then we compare the two base factors. So we compare directly the two models of interest. But we have a technical problem. The technical problem is that, remember that when we test against the value, what JASP does is to put as a prior a spike on that value. So basically the null model is that there is a spike on minus 53. And the alternative model is there is some distribution, a Cauchy distribution, and the values are around that value, minus 53. Now, when we do the same with minus 56, again, there is a spike on minus 56 and the distribution around minus 56. So the alternatives are not the same. The alternative in one case is around minus 53 and in another case around minus 56. So these are two different marginal likelihoods that we are going to find. So we need a trick. We need to make that those alternative models which that they are around, one is around minus 53, the other one around minus 56. Those distributions, we have to make them so flat that they will become actually the same distribution. And we can do that by modifying the prior. So the default prior is the Cauchy distribution with scale 0.707. And I told you before that this value is higher, then the distribution will be flatter. So the maximum value that JASP allows there is 2. So now we have the prior for minus 50, sorry, the prior for the alternative when we test minus 53, and the prior for the alternative when we test minus 56, they will be the same. So then we compare the base factors we obtained. One extra thing, I want to know the null over the alternative. Usually we want to know the alternative over the null, but in this case I want to know the null over the alternative. So let's tick BF01 instead of BF10. Okay, so we did the minus 53 and we got a base factor of 0.178. What we need to do now is to do the same with minus 56. Okay, so we change there, we press, and the base factor for minus 66 is 3.368. So the base factor is higher for the minus 56 model than the minus 53. But how much higher? Well, we have to obtain now the base factor of those two models, a ratio of the base factors. So we've got 3.368 for minus 56, 0.178 for minus 53, and we obtain a base factor that compares these two models. So 3.368 divided by 0.178, and that's 18.9, almost 19. So that basically says that the model that predicted a minus 56 difference between poverty and gardening is 19 times better at predicting the data than the model that predicted a difference of minus 53. So that's our conclusion. The model minus 56 is a better model than minus 53. So we've got some strong evidence in favor of that model relative to the other. Okay, so now hypothesis testing. We start with NHST and then with the base factor. We are going to use JASP for both analysis. So for the NHST, we are going to go to ANOVA, then repeated measures ANOVA, and I'm going to show you. I said a long time ago that for parameter estimation there were two options. One involved creating a new variable, and I show you that, but the other one involved using the post hoc test in the ANOVA analysis. So now I'm going to show you the ANOVA analysis and I'm going to show you that. Okay, so we are going to use the data, the raw data without different scores. Now we go to ANOVA and repeated measures ANOVA. So we got the variables here. So first of all, we need to define the factor. Let's call it documentary. And we know that we've got the 4 levels, and in the first level is poverty. Level 2 is for gardening. Level 3 for cooking. And level 4 is success. Okay, so now just created these repeated measure cells. Now we have to match it with the variables that we have. So remember, happiness W1 for poverty, W2 gardening, W3 cooking, and happiness W4 success. So that will calculate the ANOVA. And also I said I'm going to show you in post hoc tests. We put documentary on the other side, and here we have the mean differences with the standard error. So that's the other way of obtaining the standard error, to calculate the 95% confidence interval of the differences. Okay, so but this is for null hypothesis testing. This is what matters, and I have it in the slide. So we've got the a number of aspects here. So this is the model documentary. So that's the sum of squares of the model. That's the sum of squares not explained by the model, but there is another extra residual sum of squares, which is the between subjects residual. So basically this is the amount of variance that is not explained by the model. So this sum of squares is not explained by the model, but it is explained by the differences between participants, right? So basically this is an advantage of repeated measures ANOVA, because when we calculate the F score, instead of calculating, so basically if we I explain this again. The sum of square total will be the sum of square of the model, the sum of square that is not explained by the model or the differences between participants, and the sum of squares that is explained by the difference between participants. So that's the sum of square total, these three sum of squares. Now, when we calculate the F score in the between subjects design, we had only one residual component, which let's say is the sum of these two. But here in the within subjects design, we left that behind. So when we calculate the F score, it would be the mean square of these, explained by the model, divided by this one. So if you divide by a smaller number, the F score will be higher. and the higher the f-score, the more likely the differences will not come from a population in which the null hypothesis is true. So that's another advantage of the repeated measures analysis. So that's my recommendation. Whenever you can, use within subjects design. Okay, so these are them, sum of squares and the degrees of freedom. You can see degrees of freedom 199 because there are 200 participants, so it's 200 minus 1. And then the mean squares. So mean squares is sum of squares divided the corresponding degrees of freedom. Same for here. And then the f-score is the division between this and this. And that's the f-squares. That's very unlikely. It's a very high number, very unlikely that comes from a population in which the null hypothesis is true. And here, because the residuals are very small, eta square and partial eta square, they don't differ, but they will differ if these values are larger, because one takes into account the whole error and the other just this. So that because they are so small in comparison with this number, then they are the same number, but they are technically calculated differently. Okay, so the last analysis is the Bayes factor using JASP. Okay, so we do something similar to what we've done before, but in this case we are going to use the Bayesian analysis, not the traditional. Okay, so we go to ANOVA, and instead of going repeated measures ANOVA, we go Bayesian repeated measures ANOVA. And we have to do the same as before. We define the documentary and the levels. Level 1, poverty. Level 2, gardening. Level 3, cooking. Level 4, success. And then now these cells were created and we put happiness 1, happiness 2, happiness 3, happiness 4, and we get the Bayes factor here. So here is Bayesian repeated measures ANOVA with the Bayes factor, and you can see that the Bayes factor for the model with documentary is a huge number, and it says the null model includes subjects. So basically, is documentary with all the subjects dummy variables, like we did in the model comparison approach, the traditional maximum likelihood, against a null model that also includes the subjects. And let me just show you this in here, and this is the last analysis of a case in which one nominal variable affects a numerical variable and within subjects design.